All right. Yes, so good morning, everyone. As usual, I hope you're still dealing with all this situation very well. Again, feel free to contact me if there is any problem going on. I heard that there were some issues with the Dropbox, so I hope it's solved now in terms of space and also in terms of access. So if some of you don't have access to the Dropbox, please send me an email and I will make sure you have access to it. Another word I would like to make is that normally, we organize a visit for you in Bordeaux so that you can visit several labs and teams outside Paris as well. Unfortunately, I think this year it won't be possible, at least in 2020. So if we do it, it will be in 2021, let's say early January. And we will do anyway a doodle for that. And if you're not interested, there's no problem. Okay, so we will discuss that later. And so before we start today, I would like to show you the book of the day. So this is a book called Scaling, and it's written by Mr. Barrenblatt. It's a pretty thin book. So it's one of my favorite books, in fact. Very elegantly written. You understand all the concepts of scalings, self-similarities in physical problems, and also the connections with renormalization theory as well. So I encourage you to have a read. There is an extended version of it by the same author, which is this one. And it's a much secure object, okay? As you can see on the picture, this is an image of the mushroom of a nuclear bomb. And if you remember, Taylor was able to estimate the power of the bomb, which is a very difficult problem, only based on two pictures that were published in a newspaper. So in a newspaper, you had the two images with two different times, that's all, and with two different mushrooms. And just from those, and by scaling arguments, he was able to estimate very precisely the nuclear power, which actually is, breaking a military secret. So it's very interesting. And the physics behind the description of that is normally very complex in terms of equations. But due to those scaling arguments, you can do a lot of very nice things. All right, so have a look at it. It's very useful in soft matter in general. And now we will start with the topic of today, which is to deal with neutron scattering. So you have here a famous article where they apply the method of neutron scattering in order to understand the structure of soft matter. So again, here the example and the leitmotif is polymers, but you can do that for any colloidal system. And what we would like to do today is to describe the principle of Newton scattering in a very general situation. So I will remember in particular the links with the structure factor and the pair distribution function. And at the end, we will apply it to one particular case of soft matter, which are polymers, but you can use it for plenty of other things. All right, so please take this with you and we will switch to the whiteboard now. Okay. And again, feel free to interrupt at any time, orally, please. All right. Okay, so the tutorial is about this technique of neutron scattering. So here is the idea. You have some object which lives in a certain volume, V, and inside this volume you have several constituents, components, particles, for instance, or monomers if you think about a polymer. And you would like to study the structure of that sample from the point of view. I see there are messages. Please use don't use the chat because with the whiteboard I don't have access. The book. Okay, so just interrupt me orally. It will be easier. So here is the book. I don't know if you see it properly now. Up. Yes. So it's scaling. Okay, that's the short version, and the longest version is this one. The author is always Barrenblatt, who's that guy here. Okay. All right. Okay, so let me go on. So we want to study the structure of that system, but we don't know actually what's inside. And so we will shine some neutron beam on it. And from the scattering amplitude and the intensity detected, we will infer the locations of the particles inside and many microscopic informations. So what we want to do is to send some beam here. So we can model that as a wave. It's described by an amplitude and some phase like that. And in fact, we will assume that it's along the x direction. So if I define some coordinate system like that, in fact, the amplitude will be described as. All right, so it propagates, it's monochromatic. We will discuss it later, but those neutrons, they are called thermal neutrons. So they just come out of a box at a given temperature, and then there is a collimator so that it's really along one direction. And then they interact with the source here, the sample, that is re-emitting light. So we can, for instance, define some origin of phases that is arbitrary, where in particular we have an origin here. And all those particles, they are associated to a certain vector for the position. So J is the index of the particle, and it belongs to 1 and n. Again, n is a very large number a priori. You have a macroscopic sample. And then we want to collect the re-emitted information somewhere in space, very far away a priori. So this point, if we describe it, so this is up position R in the far field. Okay, and so we can associate it each time a wave vector. So in this case, you have a vector kj, and here you have a vector k prime. If k was the initial incoming wave vector. Okay, and we can define as well an angle. So let me just define the x-axis again. And so the angle between the incoming beam waves vector and the output one is called theta. Okay, so we've defined everything. We can also introduce a shift in wave vector. So k prime can always be defined as k plus a vector q. Okay, we put all the unknown in q, and as you can see on the blue part here, it can also be normalized as it's basically along the vector r divided by the norm of this vector, and the amplitude is k. It's k. We will discuss that in a minute, but we can just describe k prime this way. All right, and finally, I think we have described everything. And the main idea that we will pursue here is that you have this incoming wave front. It's a planar wave. It interacts with many scatterers that will re-emit S wave, meaning spherical waves. Okay, so it's pretty much like what you did when you studied diffraction in your studies. So we'll do exactly the same, apart from the fact that we are dealing with neutrons. And so we will hide all the complexity of the neutron interaction with the atoms, or all those elementary objects, by a scattering amplitude. And so, for instance, the green beam here, we will be associating to this beam an amplitude. It's an amplitude of probability of interacting with the neutron, calculating all the details of the interaction, and then re-emitting spherically this, okay? All right, so let us start now. If you don't have questions. Okay, so we will start by describing the scattering intensity. So this is the first part. And first of all, we would like to make an estimate. So we are dealing with thermal neutrons. Those are thermal, meaning that their energy is typically provided by kBT. And at room temperature, this is 300 kelvins times something 10 to the minus 23. So it's typically 10 minus 21 in joules. So if you want to put that in electron volts, when you have a factor 100 here almost, so it's like 20 milli electron volts or something. Okay, so it's in the MeV range. So it's a very low energy neutron, if you want, compared to the high energy neutrons you might encounter in particle accelerators, for instance. Okay, those are just simply produced by the thermal agitation. this is the energy, and thanks to the equipartition of energy, we can estimate the velocity of those neutrons. And it's, if their mass is m and their velocity v, you can, as usual, estimate the velocity as kbt over the mass. And so it's the square root of, if I put orders of magnitude, so we have 4 10 minus 21 for kbt, and the mass, it's a neutron. So the neutron is 2,000 times heavier than an electron, and an electron is 10 minus 30 kilos. So you have 2 10 minus 27 here for the mass. So if you neglect the prefactors here, you end up with 10 minus 10 to the 6 with a 1/2, so it's 10 to the 3, and in meter per second. Okay, so you see the velocity is like 3 times the sound velocity. So they are pretty fast still, despite their low energy. And so from that velocity, we can estimate the impulsion, the momentum, linear momentum. And from the linear momentum, with the de Broglie wavelengths relation, we can estimate the wavelengths. And so the wavelengths will be the typical resolution of that method, if you wish. So let me take another whiteboard. The impulsion or the linear momentum will be given by the de Broglie relation, okay? And so the wavelength is h over mass times velocity. And so if you put orders of magnitude, the Planck constant is something like 6 to the minus 34. The mass is, we said, something like 2 10 minus 27. And the velocity is 10 to the 3. So you have 10 minus 24. So it's something like a few angstroms. So that is why it's an interesting method, because you have wavelengths that is angstrom-like. So it's much smaller than typical optical wavelengths that are in the several hundreds of nanometer range. So it allows you to have access to smaller structures, and in particular to have really the configurations and the microscopic sizes of your sample. So that is why neutrons are used. Okay, so then another important aspect of the interaction we mentioned here, when this beam, this thermal beam of neutron is touching the sample, you have a certain probability of interaction that is hidden in B, and then you have a re-emission of spherical wave. However, we might question the conservation of energy here. Do you have losses or not? And we assume here that we have purely elastic collisions, meaning that the energy at the beginning is the same as the energy at the end. For the re-emitted beam. And so in particular, you can say that whatever the object and its re-emitted wave, the norm will be equal to k, which is 2 pi over lambda. This comes from the fact that the energy is provided by only the kinetic energy. You have no potential. Once the interaction has been performed, far away, you only have purely kinetic energy. And so if you have a conservation of kinetic energy because it's an elastic collision, then you see that the norms are conserved. And so this should be equal to E, which is h bar squared, k squared over 2m. All right? The mass didn't change, and the rest are constant. All right, so we have an elastic collisions, which means that whatever J, all the wavelengths are conserved and they are still equal to the initial incoming wavelengths. That's the elastic collision part. All right, so I told you in the introduction that we introduce a certain vector Q here. Basically, we are putting a detector at this location. Okay, this is a detector that is watching really or collecting all the re-emitted beams at a certain angle theta. You can, of course, change the position of that detector. And we can really define immediately this K prime vector purely geometrically. So since you know K originally and K prime, so let me just stress that K here is K ux, if ux is the unit vector along the x-axis, then you can immediately define k prime as k plus a certain vector q. Okay, so q will be really the quantity of interest, is kind of equivalent with the angle theta. Those are two ways of characterize the direction of detection. All right, so q is simply the difference between k prime and k. And so the norm of that guy, well, it's that quantity. And so you have k prime squared plus k squared minus 2 k prime. All right, and so remember, we have an elastic collision, so k prime is equal to k. By definition here, k prime was equal to k along the vector in blue here, the unit vector in the blue direction. So this is 2k squared minus 2k squared, and the angle between k and k prime, which is theta. So this can be rewritten the following way. You have 2k squared 1 minus cos theta. And again, this can be recast into a square. So it's 4k squared. If I divide by 2 and multiply by 2, and I recognize the sine square of theta over 2 by trigonometric relations. Okay? So this is the norm of this vector q squared. And so the norm itself is the square root of that. So q is equal to 2k. And what do we have? Sine theta over 2. Stated differently, if I replace k by 2 pi over the wavelengths, you have 4 pi, the incoming wavelengths, and simply the angular direction. So you see, you end up with the fact that the norm of this important vector q is in fact completely associated to the angle of detection. So you can really change variables, but what is important in this detection principle is that you will have the possibility to change the angle of detection, and this allows you to change the wavelengths that you are scanning in Fourier space, in a sense. Okay, so you have really a bijective relation here. The theta angles are limited to alpha plane. All right, so now comes the diffraction principle. So the idea is to say, again, that those thermal neutrons, they come on the sample, they interact with the sample, and each particle that is interacting with a neutron will have a certain probability to re-emit a spherical wave, so really in all directions. So we will simply say that far away at this position of the detector, we will simply get the sum of all the spherical waves re-emitted by the sample. This is exactly what you did with diffraction in optics, in angular optics. And we will do the same, and we will do the assumption that we are looking at very far away compared to the typical distances between the atoms or the components. If you want, we are in the far field, and we look at a sample which is much smaller in size compared to the distance we are looking at. Okay. So this is the large field approximation as usual. So let's think about this guy. So this guy has received a certain neutron that is arrived along X here. There is a certain probability of interaction that is Bj, and then there is a re-emission in a certain direction towards the detector, and we are really looking at that part. Of course, you have rays that are going everywhere in a spherical fashion here. And so we would like to compute the amplitude at that point. So first, the origin of phases has been randomly chosen at this plane, okay? So we need first to accumulate some phase before contacting the J particle. So it is pretty clear that phi J will be proportional to at least the incoming amplitude. I'm only considering the spatial part here. I neglect the time dependencies because they will vanish at the end. The frequency is the same. for incoming and outgoing beams, and so they will vanish when we look at the intensities. So let me just look at the spatial aspect. So I first accumulate some phase, which is the fact that I need to join the contact point. Okay, so I touch RJ, and so I accumulate the phase to go there. That's the first part. Then I have a certain probability of interacting, which is recast in this scattering length, Bj. And then I re-emit a spherical wave. So I have a spherical wave, and the spherical wave, I'm interested in the part that is going to the point R. So the distance will matter. It's R minus Rj here. So you have only the norm of that matters. And as a wave vector, you have Kj, which is the wave vector of that green beam here. Okay. All right, and it's a spherical wave. It's a S wave, so you really have also the distance appearing here. All right. Any question on that? No? Good. So now we will do this is an exact formula, but we will do an assumption. We are in the far field. So in the far field, basically we want to say that this is very close to vector R in norm, and that the J doesn't matter too much. So we will do a Taylor expansion of that quantity. Let me take the square, it's even easier. So you have R squared minus 2R scalar Rj and plus Rj squared. All right, and so if I'm interested in the square root of that, this will be, so let me just recast this by factorizing R squared in front. And so I just take the square root of the previous expression, and I end up with, again, that part. Okay. And then I can Taylor expand that and stay at the first order. So this is typically R minus, so this term is an order 2-1, we neglect it. There is, sorry, a square root here. And here you have a 1/2 that appears, so you have R minus R scalar Rj over R. All right, and you have then corrections at order 2. But really, the first order correction is sufficient because we already have something important, which is a dependency in the positions of the atoms. Okay, stopping at the 0th order would not be very nice because you would completely lose all the information about the structure of your material. So the first order is the one that contains the information. So we will stop at that one, and then we can just use that approximation and plug it into the previous result. So now you have this approximation. So for the exponential part over the linear term here, what we will do is that we will keep the first order in the exponential, and we will stay at 0th order in the amplitude because the amplitude is very slowly varying compared to the exponential. The phase is the important one. So what we do here at leading order is the following. We keep both terms here. And then as a norm, we have typically R. Okay, we keep only the 0th order. All right. Any question on that? No? Okay. So a few comments. this guy, we know that you have, yes, please.
Isn't there a kj on the exponential?
Yes, correct, thanks. Here it's multiplied by kj. Thanks. So this guy is equal to k because we have elastic collisions, remember. Okay, all the wavelengths are equal, so lambda j is equal to lambda, same for k. First part. So this doesn't depend on j explicitly. The dependency, and then we have another thing that we recognize here. Again, this is k. So we see you have k times vector r over r, and this is the definition of k prime here. So we can just plug it here. So this is a0. You have rj here, and you have r at the denominator. You have bj, sorry, ikr for this part, and then you end up with exponential minus k prime times the vector rj. It's a scalar product. All right. And so now I can group, I recognize that you have rj here and rj here, so I will group the two and make the vector q appear, and the rest will follow. So the approximate amplitude is a naught over r exponential I kr. This is really the spherical wave as if the sample was a single point. Okay, so you don't have structure in this term. You have also an important part, which is you need to have a scattering amplitude, which is a length, so that you really counteract the length that is at the denominator. And then you have the structure in the phase of the material. So if you look at what is here, you have minus k prime minus k. So this is q. Okay, so this amplitude is common to any j, any little particle. You have a prefactor, which is simply the proportionality factor, which is the probability of interaction. And then you accumulate a phase that depends on where you are in the sample. So this is the structure information you want. And this is, I think, the equation you have in the tutorial. Yes, okay. So now, from that amplitude, we might be interested in the energy aspect, the intensity, okay? So we might first compute simply the total amplitude, let's call it psi. Total spatial amplitude will be the sum over m of the psi m, okay? And the intensity will be simply the squared modulus, so the sum over m and n of complex conjugate and psi n.
Excuse me.
Yes, please.
Yes, when you say that you accumulate phase, what do you mean by this?
I mean that, so first look at this prefactor. This is, in fact, if you look at that part, it's a spherical wave starting from the origin, 0, and going at a certain distance r. Okay, so it's a spherical wave that is everything as if you were basically touching that point with incoming neutrons, and then that point re-emits, it's a single point, and it re-emits spherically some amplitude. But there, you don't have really a structure about the sample. The sample is really connected to the position rj. So in the correction factor that is here, well, you have access to all the positions of the components of your sample. And this is, for each of that position, you have a different phase. So now you see you're accumulating phases that are depending on the position of the atoms. That's what I meant. Is it clearer?
Okay. Yes, thank you very much.
Okay, so so now we have that amplitude. We want to go to the energy, so we just take the squared in a complex world, and you have this object, and so we can write it. So you have, let's assume that the amplitude is real. It's just here a choice. We can assume that this guy is real because we've defined the origin wherever we want. Okay, so there is no phase associated to it. So it's A0 squared divided by R squared. That common amplitude will vanish if you take the modulus. It's of modulus 1. Then you have the sum over Mn. You have Bm star. A priori, those numbers, they are complex. We will simplify this statement in a minute. And then what do you get? You get Rm minus Rn. Okay, so already it's interesting. In the energy-like quantity that is here, what you get is now information about all the distances between all the particles. So you're really now starting to get the information about the spatial organization of your system, as I was explaining before. So now it's in the energy part. And now just in terms of definition, you are sending a beam in a certain direction of detection theta or q, but then you have an element of solid angle around that you can really probe with your photodiode, for instance, or photodetector, and therefore you need to take into account the solid angle as well. So we will define a certain energy as this, and so you are in the far field. So the element, you have the R squared d omega, where omega is the element of solid angle. Okay. So basically, this is now, and what I said before. Okay. And in fact, I don't really care about the R. I know the distance. I don't really care about the element of solid angle. So what I'm interested in is what we call here the scattered intensity, which is just a definition, but it can be defined as 1 over A0 squared. I just normalize by the input energy I place in my probe, in my neutron beams, and I also normalize by d omega. So all right. And so if I do that, I end up with the following formula, which is the fact that the intensity collected on my detector with a certain extent on solid angle is this one. And again, so a priori, those are calibrated scattering intensities. I know how a neutron interacts with a certain molecule. So there will be some studies for that, and we will assume that we have calibrated that previously. So there are no numbers. This is really only the angle of the detector. We say that Q was really parameterized by the angle theta. And so basically what you get by collecting the intensity on your detector is an information about what is going on inside your sample, where the particles are located, and so on and so forth. So it brings me to this final point for that part. What is the resolution of that technique then, according to you? According to that formula. What is the argument? Yes.
If we are very, very far away, it's we can be very precise, exactly precise.
So can you comment mathematically on that? Where do you see? So here I'm collecting a certain intensity on a photodetector, okay, or neutron detector, and I have this formula. Those are numbers, Bm and Bn. Where do you see the far field aspect here?
In theta, which is in Q.
Yes.
So if we can go far away, then with more precision on the measurement of theta.
Okay, so now I understand what you mean by far away. You mean large theta, for instance?
Not large theta, but good precision on the value of theta.
But it's not far away, no?
Because if we can move, for example, of 1 millimeter up or down our detector,
Yes.
and we are at 10 centimeters, we are not very precise on theta. Well, if we are 10 meters away.
Okay.
Move one
So first aspect, it is correct. I might be very imprecise in my theta estimation. However, as you will see, and as you've seen already in the tutorial, what I have is typically a trigonometric function, which is a sine or a cos of theta. So, you know, this is a function that is pretty smooth. It is true that the further away I am, the more precise I'll be on theta, but this is telling me the precision on Q. It tells me how precise I am on Q. It is true that you might do errors on that, but let's assume I'm perfectly good in the theta estimates, meaning 0 error in theta. Still, what is the precision of this measurement? What is the resolution? It's associated really to the neutrons we are using.
Lambda.
Yes. So the argument, as we said before, is lambda, but we see it here directly. This phase, when it accumulates a value of 2 pi, then you have a notable variation of the phase, you could say. Okay, so typically you can say that the resolution is when Q times, let's call it delta R. This is my spatial precision, if you want, will be on the order of 2 pi. When I have accumulated 2 pi, well, I mean, I varied my cosine or my sine sufficiently here in the phase, and so this implies that Q. Remember the expression of Q. I will write it in norm. It's equivalent QR. Okay, and Q is 4 pi that we demonstrated over lambda, and then you have sine theta over 2. When this is equal to 2 pi, you have your resolution delta R. Okay, so we can simplify further, and delta R will be provided by lambda over 2 sine theta over 2. In a world where I have a very precise definition of theta. It's true that I might also have errors on the theta estimate, but I might also have errors on the lambda estimate. You know, there is a bandwidth on my neutrons. Okay, I assume those are parameters that I manage and that I know how to properly work experimentally. Still, I have a resolution which is delta R, and which is in the best case when you reach 1 here. Okay. So you have a lambda over 2. So the best resolution I can have, meaning the smaller delta R, is typically lambda again, and we say that it's angstrom-like before. So we recover the intuition that the wavelength of the beam you are using will be your elementary resolution in space, but you knew that from optics. All right, it's probably a reminder for you, all of this. Okay, any question? All right, so now this was for the optics aspect. Now we would like to move on to the theory of liquids, and what do we learn from this intensity? So we are really collecting the intensity at a certain angle theta. We can, for instance, average that intensity over a long time and get some signal. What do we learn? I mean, how do we connect that to, for instance, to density fluctuations in your liquid? You have a sample of liquid with plenty of atoms that are moving all around. You average that, but what information do you really get? And we would like to connect the intensity collected to some important observable in the theory of liquids, in particular, what we call the pair distribution function. So this is the goal of part number 2. And so we do 2 things. We will assume that we have an homogeneous liquid state. It's liquid, it's equilibrated. It's not a glass material that is very longly evolving or slowly evolving. It's really sampling equilibrium, so you don't have problem with canonical averages here. And we will also assume that all the scatterers are identical. So all the BJRB. So you have really an homogeneous system made of identical particles. Okay. You could refine that if you want, but it's not needed to get the first ID. And we will assume that those are real numbers, real and positive, or okay. We don't consider the phases there. Okay. All right. That's the first part. And In addition, we recall an important object in the theory of liquids, which is the pair correlation function, pair distribution function. And so it's basically the correlator of the density rho at one point r with the density rho at another point r prime in space. And just to subtract the self part, there is this term if you open a book of theory of liquids. And also there is a normalization aspect, which is basically the density squared. So you have something like that. The single densities averaged. Okay, anyway, this is an observable that is found in textbooks about the theory of liquids. And basically the essential aspect is the fact that it's mostly given by the correlation in density. I take 2 points in my samples, 2 points in my sample, and I would like to see what is the correlation between the density there. So the density is fluctuating spatially and temporally, and we would like to know that. Okay. And yes, this is a Dirac. And the averaging that I'm using here is really over several realizations. So it's at equilibrium. I just sample plenty of configurations. All right. Okay, so we introduce a notation that is the structure factor. So we have the intensity collected on the detector, which we found, and which is a function of Q, a function of the angle of detection. All right. This is instantaneous in a sense. Okay, so what we can do is let the system, the liquid you are studying, for instance, in your sample, that is, let it evolve in time so that it explores the phase space. And so you can average that over various configurations. That's the first thing you would do typically experimentally. First of all, because you have a certain averaging time in your detection procedure electronically, but at the same time, also because it's important for the system to be equilibrated. So you do that, and for normalization purposes, it's purely a convention. We introduce a quantity that we call the structure factor, which is simply the ratio between this average intensity divided by n times b squared. So this is a pure convention. You could remove that, okay? All right, and so remember that the intensity was the sum over m and n. You had bm star bn, so now it's a b squared. And then you have this exponential IQ RM Rn. Now, if I normalize by b squared, I end up with the 1 over n, and then I can invert the sum and the average. And basically, I just end up with the average of that exponential phase, okay? Sorry, typo here. This is what we call the structure factor S. But basically, there is no more information than in the average of your intensity you detect experimentally. So we will understand why it's the structure factor, but you already see that it contains the structure. Okay. All right. So now, how to connect that to that function G? That's the goal of what we want to show now. So according to you, what is the definition of the density at position R for this system? You can assume that you have like point-like particles in your liquid. So what is the definition of the expression of the density at a given position R?
It's a sum of Dirac peaks. So it's the sum of all G of delta of R minus RG.
Yeah, correct. So you could say that, well, it's the sum over all particles. Remember, going from 1 to the total number of particles. Okay, so it will be correctly normalized to the number of particles. And it will provide an infinite peak when you are touching a particle and zero otherwise, really. Okay, so that's the mathematical expression that we want to use. And what is the average of that? Well, let us define the average first. So the average, we are really in a liquid that is uniformly sampling all configurations. Okay, there is no special trap or and so on. So the average of the quantity point here will be by definition the integral of that quantity over all possible R. So this is a triple integral in 3D. And you normalize that by simply the integral over R, which is the volume. So the average density is that stuff. And so you have the sum over, if I use the definition here, over all particles, the sum of Dirac's divided by the volume, okay? And well, this will give 1 for any J, because we are already scanning this in the volume of the sample. So I'm sure I will find all the particles. Sorry, I see that there is a chat here again. Let me open it. Sum I delta. Okay, so please do it orally if you can, if you have a microphone. It's easier for me because with the whiteboard I don't see the chat. Okay, thanks. So this is the sum of 1 over V, and thus you end up with the average density, which is as expected, the number of particles divided by the volume. I can give it a name. It will be the average value rho naught. Okay. Then we would like to move on to G. So remember, the expression of G for 2 given points in the sample, the pair distribution function is given by the average of that product minus the self part and then normalized by the products of the 2 average densities. So first we assume that the sample is homogeneous in space, so it means there is a translational invariance, if you wish. So I can really first rewrite without loss of generality, or I mean I can compute G at a distance r minus r prime and 0 for previous r prime. This is just applying the previous formula at those specific points. For now, I'm not doing anything. In fact, there is no assumption here. All right, and this doesn't change. And I normalize by the product of the average densities and rho naught. And now comes the assumption of homogeneity. So finally, just let me do one more thing. I can really change variables and call that R. The distance vector is called R. It's just a change of name. And I can also call it, in fact, G of R. Should change the name of that function, but you understand what I'm doing. All right. So this is just a change of variables. There is nothing special here. But it's only a function of the distance, R. Okay, but now if we have an homogeneous sample, what do you think about, for instance, those 2 factors in the denominator. The average density at one point and the average density at the origin, meaning average over plenty of configurations. And the same for this guy. What do you think? Well, we discussed that previously. The density at one point is rho naught, and it doesn't depend on which point you are looking at, which position in the sample you are looking at. So it doesn't depend on R anymore. And so those quantities, the density at point R average over plenty of configuration is exactly the same as the density at point 0 average over plenty of configurations, because you're dealing with a homogeneous liquid at equilibrium. Okay, if you have a structure and something, a crystal or a glass, this will be different. So those are constants, rho naught. So thanks to that homogeneity assumption, you end up with a simplified expression, but basically it's exactly the same main ingredients. Rho naught, a Dirac centered on R, and then rho naught squared. Okay, so it's just a simplification of the above quantity, but you still have the correlation in density between 2 points distant from a vector R, a self part, and a normalization. The important question is not that, is how can we relate that quantity to S, the structure factor? Sorry. So here we go. So S of Q, we said, it is recalled in the tutorial. We ended up with that formula is the average of exponential IQ, the distance between the 2 points, Rm and Rn. So question, now we need a trick to transform that into a density correlator. So does anyone see how we could proceed?
If we do a Fourier transform, we get delta functions.
Yes, so that is correct. So we can let me just transform what is inside, and you will let me know if you agree. So you have this average, and I can just keep it, and I will transform this exponential into, in fact, the integral of a Dirac, double integral of a Dirac. So you have d r prime dr exponential IQ r minus r prime, but picked at r minus rm, r minus rn, sorry, r prime minus rn, and up. Okay. This is what you had in mind, right?
Yes.
Fourier transform of a delta. Okay, and so now the next trick is to take that sum and invert the average and the integral that are also linear operation, and so bring it there. Again, those are triple integrals over the vector R in space, over all the sample, in fact. And then I have sum over m's and then sum over n, r prime minus rn. And then I should close everything. All right. And then question, what is random in all this? What is moving all the time in a liquid?
The position of particles?
Yes. So all the Rms and Rns, okay? The rest, those are deterministic variables. they are integrated in R and R prime. Q is what I fix as an experiment list, and so on and so forth. So the only average quantities are the M and N stuff. So basically, I can also put it back here, and I end up with 1 over N as dr prime. So it's a Fourier transform of something. We'll discuss in a minute. And then we end up with the correlator of two stuff that you recognize now pretty well, the densities. Okay, we say that this is the density at point R, and we said also that this is the density at point R prime. So in a sense, we are saying that the structure factor, apart two prefactors here, 1 over n, etc., is in fact the Fourier transform of the density correlator. So what I measure on my detector optically, or with neutrons, is related to the correlation of densities in the sample. So really an important statistical physics quantity to describe the structure of the liquid. So I can rewrite it this way to summarize. S is equal to the Fourier transform of what? Of the density correlator. So now let me just do one more thing first, if I may. I will just use the assumption of homogeneity again, because it's too long as an expression. So dr prime, I just rewrite it very quickly. And then you have rho r prime. Okay, and now I would just like to change variables. So before doing so, the homogeneity tells me that this is equivalent to shifting everything by r prime. So I can say that this is equal by homogeneity to the average of the sample is the same if I shift all the position by a certain amount. And so the correlators are the same, okay? On the statistical aspect, I mean. Okay, so I can do that, and this comes from the homogeneity aspect. I shift everything by r prime, and now I make a change of variables. This is capital R. This is capital R, and I can integrate over capital R, for instance. So by change of variable, I have dr prime, d capital R, IQR, and the correlator between the density at R and the density at the origin, whatever the origin is. Okay, and you see that there is no R prime dependency anymore, so I can really transform that into a volume. So you have V over N, which is the inverse of the average density, in fact. So you have 1 over rho naught, and then the Fourier transform, all that part, the Fourier transform of the density correlator. So Fourier transform of rho R, rho naught, average, which is at the end not anymore a function of R, but a function of Q. So this is what you collect on your detector after averaging and normalizing correctly, and you end up with the fact that what you collect on your detector, apart from a Fourier transform operation, is in fact the density correlator. Okay, so now you understand how you get information about the structure of your liquid or your soft material if it's still at equilibrium. Then we want finally to conclude and relate G, not the density correlator only, but G, the pair distribution function, to S. So it's pretty immediate now. If we recall, where is the expression of G? We will start from that quantity. So we take the Fourier transform of that, so that it makes the Fourier transform of the density correlator appear and we know it. It's related to the structure factor, and the Fourier transform of a delta will be 1, so there will be just a shift, an offset. So let me take the Fourier transform of G of R and thanks to the above formula, you have the Fourier transform over rho naught squared of the density correlator. So it's rho 1 over rho times S. Rho naught, sorry, thanks to that formula. And then we have a second term, which is 1 over rho naught times the Fourier transform of delta. So it's 1 over rho naught. And this, I could have called it the Fourier transform. Let me change the notation. The Fourier transform of G is called G hat. It's a function of Q, the wave vector. And so if now I just play with this expression, I end up with the fact that the structure factor is in fact 1 plus the average density times the Fourier transform of the pair distribution function G of vector Q. And this is the central result, I would say. So again, you have your sample, you send some incoming beams, your sample is sending plenty of information everywhere, you put a detector somewhere, and you record the information and you average it over time so that you average, in fact, the configuration of your sample itself, okay? By averaging the intensity collected, you construct S. But in fact, what you have done is you immediately obtain, in fact, apart from a prefactor, which is the average density of your system that you can measure, okay, for instance, you get the Fourier transform of the pair distribution function. So you get the pair distribution function. And this is an important aspect of the theory of liquids. It gives you all the correlators of densities. Okay, do you understand what we've done so far? I mean, don't you understand what we've done so far? Is there something you didn't understand? Any question or comment? No? Okay, so now you understand the principles of that technique, and we would like to finish by illustrating it on a very specific example, a polymer chain in a solvent. And so basically we take a glass with dilute polymer chains inside, and we shine neutrons on it. We put the detector and we collect the signal and average. And we would like to see if we are able to find some important statistical information or even microscopic information about the polymer chain. The size of a monomer, the number of monomers, for instance, okay? And so this is the goal. And if we succeed in that, it will show that this technique is really interesting if you want to look at the fine structure of soft materials, and liquids in general, but soft materials for us, okay? So let us apply this to polymers, because now you have a good knowledge about what is the statistical distance between two monomers in a polymer chain, because you've done all the statistics already. So it's a good way to connect to what we did so far as an illustration. So let us apply this to polymers. This is part number 3. And now our sample is in fact, again, the same volume, but inside you have connected object. And again, it's made of, I won't draw all of them, but you have a certain large number of monomers, and each with size of a monomer. Okay, and so now we have that sample, and we shine neutrons on it.
So
yes.
We are counting on the fact that B for the monomers are not the same or very different from B for the solvent.
Yes.
Okay.
We know them, in fact. We know all of them. And second aspect is that you could have a shadow imaging. You could have a sample where there is no chain, where you have pure solvent, and then a solvent where there is a chain or a dilute assembly of chain. And so by subtracting the two signal, you can remove like, you know, the unnecessary information about the solvent.
Okay.
But you're correct. What I did so far is to assume that I have only one species and some kind of vacuum around, but you could, I mean, modify this by saying, well, now I have two different types of species or three different types of species. And in fact, those techniques like neutrons, but also X-rays or whatever energy you want and size you want to infer. In fact, this is very interesting to have the composite aspect of a structure. You can have plenty of different particles, oxides, different atoms, and you want really to locate specific structures. So it's not necessary that you look at very homogeneous and unique identical objects. Okay, is it clear? Yes. Okay. So now you will have to help me and remind me how to do that in a sense. You remember the structure factor is the quantity of interest. This is what I record on my detector, okay? And I know that it is related to some important object, which is the average in the statistical sense, meaning on all possible conformations with the proper weights. For the liquid that we discussed so far, we said, well, all the positions of the atoms of that liquid are equiprobable, okay? But you know that now we are not dealing with a simple liquid anymore. We are dealing with a complex liquid. It's made of polymers. And in particular, 2 points, they have a certain correlation between them. They are connected by a certain polymer chain. And so we know the statistics of that polymer chain. So it's not anymore a simple liquid on that aspect. So we would need to make sure that we calculate this properly. And the average here is not a uniform average anymore, but it's an average on the distribution of monomers M and monomers N that are on the same chain. So there is a probability associated to that distance for a given chain. And to simplify the problem, because we want to illustrate it first on very simple systems, we assume that we have an ideal polymer chain. We don't need to complexify this by adding some effect of interactions. Okay? So what is the good probability, the good distribution that defines this average? In 3D and for an ideal chain?
Gaussian.
It's a Gaussian. We will make sure that we have the proper normalization because we have 2 points here. So 2 monomers M and N, okay? And we know it's an ideal chain that doesn't depend on the past. I mean, it's a Markovian process. So whatever M and N are, we could say that N is the starting point and M is the final point, okay? So the probability density of having Rm and Rn is in fact, as you said, a Gaussian. So remember, we have a tree for a space dimension tree, and then we have 2a squared times the number of objects. So if I have n as a starting point and m as a final point, the first monomer is n plus 1. So I have m minus n total number of objects. This replaces the capital N that we had in the previous tutorials. And here I have the Gaussian aspect, so the distance squared. Okay, so that was the Gaussian part. And I need to put back the normalization, so I need to have the variance here as well. So it's the same. There is a pi in addition due to the Gaussian integral. And for each direction of space, you have 1/2. So it's 3 over exactly this, but with a pi coming back from the Gaussian integral. Okay. Okay, the problem with that formula is that if I integrate it over the starting point and the end point, I get the volume. It's not normalized to 1. So I can also simply normalize it by the total volume to make sure it's a proper probability. And so that the averaging here is really a good average. The average of 1 is 1. Okay? No question on that? Okay, so what I want to do is basically the Fourier transform of a Gaussian at the end. But let us write everything properly. So S is equal to 1 over n, the sum on small m and small n of the average. So it's the integral over dr over rm and another triple integral over rn of that quantity. So 1 over v. Just a copy paste. All right. So again, we can do a little simplification here. So we are interested in what? Sorry, we won't keep everything. We are just interested in that quantity. So the average, this is what we want to compute. We will remove that because we want to compute only for now exponential QRM minus RN. So there is something missing here, which is and oops, sorry. All right, so this is what we want to compute. So it's the proper average, and there is again this this change of variable because we don't really need the origin here. So I can transform all those quantities into capital R. Same, this is R, and I will integrate over R. And so there will be something that doesn't depend anymore on Rn, so it will give me the volume divided by this one. So this will cancel out. Okay, so I can recast this into the following form. This quantity is in fact a simple integral over capital R of a norm and Gaussian and Fourier transform. And then the Fourier transform aspect is here. No minus sign, no minus sign. Okay. Agreed? That's what we want to calculate. And you see we have 3 directions of space. They are all factorized. So by the Fubini transformation, we get that this is in fact Ix times Iy times yz, all identical, and we will just calculate one of those. So this is the integral over dx over only 1 square root by m minus n. And here I have 3x squared over 2 m minus n s squared iqx times x. And qx, just for simplicity, I will name it capital Q so that I don't. This is I don't keep indices. Okay. So it's the Fourier transform of a Gaussian. I will go pretty quickly here, and the integral is over the total sample along x. So you have this 1/2. Then you have dx, and then we will complete the identity here, so we can transform that into the square root of 2 square root of m minus n times a, and then you have so you need a I, you need a Q, and you need to put all the rest here. Minus n s squared. All right, and the factor 2 here due to the square root of 2. Okay, squared. So let me see, and then by putting that squared of a sum, you have an extra term that you want to compensate for. So you have minus the Gaussian in Q, m minus n s squared over 6. Okay. So this is the square root of this number. And then you have the Gaussian in Q that goes outside, this x integral. And then you have something we will simplify in a minute, but basically a Gaussian. And then I can call epsilon, not necessarily a small number for now, like that. So epsilon is everything you have here. Okay. So now a final change of variables here will allow me to call this guy u. So if I do that, then dx is equal to du times square root of 2 square root of m minus n a over square root of 3 in front. And so I end up with the fact that ix let me see what jumps out. So 3 disappears with this 3. 2 a mn. All right, there is a pi that remains, and then you end up with the exponential. So 1 over square root of pi okay, m minus n. And then I have the integral of du exponential minus u minus iq epsilon squared. Was it all? Minus yes. If no mistake, this is what we have. And so now I can say that, well, u minus iq epsilon is equal to v, another change of variables. And then you have dv exponential minus v squared. It's a Gaussian. Careful now, the bounds are the previous one plus iq epsilon. So if we have a very large sample, we can say it's minus infinity plus infinity, so on the real axis, but then you have a shift in the complex plane. But there is no pole for such a function, so there is no particularity, no residue, and so on. So basically, integrating along the real axis and on any shifted axis in the complex plane will give the integral of a Gaussian. And in any case, you can do a closed contour for that. We discussed that already in the first tutorial. This is square root of pi. It's the integral of a Gaussian. And this square root of pi compensates the previous one in front, so you end up with simply q squared a squared m minus n over 6. And q was in fact qx by definition. So now I can put back the exact expression. So on the x-axis, that is the result of what we wanted to compute. That is ix. And what we want is ix times iz, iy times iz. Okay, so the result is what we wanted to compute. total vector Q Rm minus Rn for a polymer chain. So with the proper averaging will be the factor of that for X, Y, and Z. So you see that the norm of Q is appearing to the square. This is okay, the Fourier transform of a Gaussian in 3D in a sense, where Q squared is equal to Q squared. It's the norm of the total vector is Qx squared plus Qy squared plus Qz squared. Okay? Any question on that?
Yes.
Yes. Or any mistake I made, or let me know.
The vector Rm minus Rn is a Gaussian vector.
Gaussian distributed, yes.
Yes. So this average should be given by exponential minus minus Q, the average of Rm minus Rn, plus Q squared, the average of Rm minus the variance of Rm minus Rn.
I'm not sure I understand. Behind this average, so there is this Fourier transform quantity, but this average is a Gaussian. So we are doing the Fourier transform of a Gaussian. Okay? The
Yes.
Fourier transform of a Gaussian, if I have, let me go 1D for instance. If I have a Gaussian that is, let's say, x squared over 2 sigma x squared. That's a Gaussian.
Actually, it's okay because it's the average of Rm minus Rn is 0. So the first term.
It's centered. You mean it's centered?
Yeah. So it's just a formula that we could have applied.
Okay. Yeah. Of course, what we did here is just the, in a sense, the Fourier transform of a Gaussian. So now you are telling us that in fact the variables, they are centered, meaning the average is 0. And so what you recover here the Fourier transform of that is exponential minus Q squared 2, but it's sigma. So sigma, let me write it this way, sigma up Q squared with sigma Q squared is equal to 1 over sigma x squared. And so that is why you recover the Gaussian variance here, but at the numerator and not the denominator. And there is a factor 3 that is below. Okay?
Okay.
And sorry for the minus sign. So you were right. We could have applied immediately what is the Fourier transform of a Gaussian with, for instance, if it was not centered. But here it's centered, and we redid the calculation. Okay? Any other question? No? Okay, let us go on then. So that was the first part, but we didn't complete the job. What we want to do, in fact, is to calculate S. So S is not only that, but it's a sum over all n, over all m and n, I should say, of what we did, what we computed so far. So it's a bit more complex. And so it is the sum over all monomers, double sum. Okay, that's what we want to compute, and we can simplify a bit the notations, not to have too many parameters and denominators. So let me just first I want to compute ns and not s, which is the sum over mn of exponential, and then again I can introduce something like alpha. I don't care about what is alpha, but let's put it here for now. So that it's a it's a simpler problem to solve in terms of size of the expression. Any idea on how to compute that? You have two difficult aspects. The first one is that you have this norm of the difference between m and n. So depending on who's the largest, well, you might have a minus sign. So you should be careful about the bounds of your integral. So for instance, you can cut this summation for n, let's say, for n going from 0 to m, and then finish from m to capital N. That's the first part. But the second thing is that you're dealing with a discrete sum of exponentials like that. So any idea on how to simplify this discrete problem? Or transform it into an easier one? Remember that we are dealing with the Brownian limit, which is a continuous description. Stated differently, A is going to 0, the size of a monomer. So what is the trick there? Can I transform that sum into an integral easily?
Yes.
Yes, so this is the Riemann integral. Provided that the step is going to 0, I can really replace the integral of a continuous function by the discrete sum of all the rectangles, okay? This is what I'm doing. And so just now we are between physicists. So I will just write something like, this is transformed into the integral over, let's say it's a continuous variable m and n instead of the summation of exponential. But of course you understand what I'm doing. You can just, if you want to do this properly, you take the small m and the small n and you divide them by the total number of objects, capital N, so that you make really a continuous variable that is between 0 and 1. And then you do the Riemann limit, okay? But I mean, this is equivalent. So this is a good approximation of this discrete sum. And in general, integrals are much easier than sums. So we do that. We are allowed to do that because the Brownian limit is the following. You have an infinite number of objects, but their size is going to 0. So really, you are in a situation where you can apply the Riemann summation. And so this is easier to calculate. And let me just cut it in two parts and specify perhaps the bounds. And so n times s is equal to integral of m. And then I will cut the second integral for small n going between 0 and small m, and then between small m and capital N. Of exponential and then the remaining part. Up. And so finally, now that I have cut the integral into two parts, now here small n is always smaller than small m. So this is really m minus n. It's a parenthesis. And here it's the reverse. This is n is smaller than n is bigger than m, so this is n minus m. So you see that I'm left with the integral over m, and then I have still two terms. So I can put alpha n alpha minus m, sorry, alpha, and plus another integral over n. Okay. Okay. And this is not depending on small n, so I can put it in front. And same for this object. So this is rewritten in the following way. Plus end of the parenthesis. Okay, let me remove this useless stuff. Okay, so and then, well, this is what? This is alpha m minus 1 over alpha, if I integrate it. And here, this is exponential minus alpha n minus exponential minus alpha m, the bounds. And then I need to take into account the minus alpha here, the denominator. Okay. So now I can put all the alphas in front and then compute n s alpha. So I multiply the left-hand side by alpha now, so that I kill the alpha, the denominators. It's the integral between 0 and of small m of 4 terms, alpha m minus 1. Then I have minus and then plus sorry, there was I missed something here. Oop. There was a prefactor that I forgot. Excuse me for that. Okay, there is this guy as well and this guy. So let me start again. So I have 1 here. Then I have minus alpha m, exponential minus alpha m. Then I have plus, which is a minus exponential alpha m exponential minus alpha n. And then I have a plus exponential alpha m times exponential minus alpha m, which is 1 again. So I have 2, 1, so which can be rewritten between 0 and dm of 2 minus exponential minus alpha m minus exponential plus alpha m minus alpha n. Okay? Sorry, it was a bit long, but life. All right, and so now I can do this final integration. So let me just rewrite this on a novel whiteboard. NS alpha, I'm just copy pasting, so you can just wait. 0 n dm of 2 minus alpha exponential minus alpha m, and then minus plus alpha m exponential minus alpha n. Okay, and I want to integrate that now over m. So the 2 here will provide n, so it's 2n. Here I have minus the integral of exponential minus alpha m, so it's exponential minus alpha m divided by minus alpha integrated between 0 and n, and minus exponential minus alpha n, and then I have the primitive is the following, integrated between 0 and n. Okay, so if you want, I can just put pluses everywhere here and remove that quantity. And I can also multiply everything by alpha. So it's 2n alpha plus there is no more alpha then exponential minus alpha n minus 1 minus 1 and plus, which can be rewritten again in 2n alpha plus 2 exponential minus alpha n minus 2. And then I can factorize 2. Well, I won't do that now. Any question on that first? This is just algebra, right? Okay. So I'm not interested in ns alpha squared, but as you see in s over n, so s over n, I can use the previous result and just divide it by n squared alpha squared. So I have 2 over n alpha. Okay. And remember that I can introduce a variable u, which is n alpha, because apparently n alpha is everywhere in this formula, so it's the good variable. And alpha was what? Q squared a squared over 6. Okay, so this is again 2 over u, so I can just factorize 2 over u in factor of 1 minus 1 over u, that appears once here, minus exponential minus u, and that's it. So we recover what we call the Debye formula that is provided in the tutorial. Okay, if you look at your... Do you have any comments, or is there any, there is no typo on the final result, but perhaps an intermediate step that wasn't clear, or? No? So let us continue. So I told you that u, that appears apparently here as the unique variable of this problem, is n q squared a squared over 6. So u, I can rewrite it here, n squared a squared over 6 times q squared. And q, we know it from the beginning. We calculated in the tutorial. It's related to the wavelengths and the angle. So there is no n squared. Sorry about that. Let me erase this one. Okay, and this one. Ah, sorry. Okay. So q squared is 4, so 16 pi squared, lambda squared you have, and then you have a sine squared of theta over 2. So I can simplify a bit. I have n a squared 8 over 3 pi squared. And then sine squared is what? Is 1 minus cos 2 times the angle, so theta here, divided by 2. So in other words, u is 4 by 3 n a squared. I have a pi squared here too, the numerical prefactor, lambda squared, and 1 minus cos theta. That's the variable u. That is the only important one in this problem. And s over n is a function of u. All right. So how can we use that formula? So again, you're recording the intensity on your detector, you average it, so you're able to construct S. So you have S, which is apparently a function of u, and so you can look at different limits. You see, in u, you have what are your possibilities. In u, so this is a material properties, the size of your polymer chain. This is material properties, the size of one monomer. This is fixed. Let's say that you have a certain temperature in your oven containing the neutron, so they go with a speed and a wavelength that are fixed from scratch. So your tool here is theta. You can play with the angle of detection, and depending on the angle of detection, you will scan the value of u. Okay, so you can record it completely by really doing the tomography and going at all angles, and you can really check that this formula is correct, and all the free parameters will provide you what you miss, meaning n, capital N, and small a, so the length of your polymer and the size of a monomer. Okay, this you can do, and this is purely numerical in a sense because this function is complex. However, you can look at two extreme limits to understand more physically what is going on. So let's take first the large wavelength limit, so the small u limit. So limits, we will do the two large wavelengths, meaning u goes to 0, and the small wavelengths, u goes to infinity. So let's first start with the first one. So when u goes to 0 in this formula, you can Taylor expand the exponential. So let us go, u goes to 0, then s over n is 2 over u times 1 minus, so let me just copy paste again what is the expression we found. It's 1 minus expansion minus u, so you have 1 minus 1 plus u minus u squared over 2, etc. if I expand the exponential in series. Okay, so I stop out order 2 here because the first order, the zeroth order vanishes, and the second order, you see there is u and 1 over u, so there is a minus 1 that will cancel out this one. So you need to go to the second order, but then you can stop. 2 over u, and what do we get? We have minus minus, so it's a plus, u over 2, so it's 1. So good. It means that in this limit, s reaches the value of n. And remember that what you are measuring is not s, but you are recording the intensity and average it. So there is a connection that is written in the tutorial. The average of I is equal by definition to n times b squared times s, so it's equal to n squared b squared. Okay, careful, b is not the monomer size. The monomer size is a. B is the scattering length. It's the amplitude of interaction between a neutron and one monomer. Okay, it's let's say a quantum quantity if you want. So you know it because you can, for instance, first study a liquid of pure monomers and calibrate your B values. They have been calculated by quantum chemists, for instance. They are tabulated for plenty of molecules. So B is in fact a parameter. So this is known, which means that the only unknown is n. So from that limit, you measure n. This is expected because you are in a limit where, remember, the wavelength is very large. So if the wavelength is very large, what you have access as a component of the structure is the large scale quantity. So it's the total distance, okay, of your polymer chain. If you, in contrast, want to have access to the size of one monomer, you want to reduce the wavelength, meaning that you want to take the other limit where the wavelength is small and thus u goes to infinity. So this is the second limit. When u goes to infinity, remember the expression is here. So when u goes to infinity, you can just, basically you can kill the exponential here. And you have simply 2 over u as an equivalent. So you can have this equivalent 2 over u, which means that s reaches 2n over u. And remember that what we have is the intensity as above, which is nb squared times s. So n squared U over U. And I can put back what is inside U. So U is, it's provided in the tutorial, so it's 4 pi squared n a squared 1 minus cos theta. And here you have 3, so it's a 6 here, lambda squared. It's a 6. 6 over 4 is 3 over 2. And the n squared is vanishing as well. I can kill it and remove the n here, and the rest doesn't move. Okay. So in this limit, I end up with the fact that now remember I already know a capital N because I did the measurement with a very large wavelength first. So I know N. Now I want to know A. Well, since I know N, I mean I know it now. I know the interaction strength. I know the wavelength, I know the angle, and so the only unknown is A. So now I get A. So you see now by going to the small wavelength limit, I get A. And in fact, I get the full curve between the small sizes and the large sizes. So I have all intermediate length scales in my problem. Okay, so this was an illustration of the principle on how to derive some microscopic informations from a sample by doing some neutron scattering and diffraction, if you want. And there we made use of the polymer statistics to connect all these ideas. But you could have a more complex system, several polymer chains, inhomogeneous compositions, various components, as you already mentioned. And so, I mean, by doing the proper calibration on pure samples first and going towards larger complexities, even biological if you want, well, you will be able to have novel information at each step. Okay, that's the main idea. So I hope it was clear. Do you have any comment or question on that before we stop? No? Okay, so let me stop the sharing and then I think I will say bon weekend à tous, and we meet next week for the next tutorial. Don't hesitate to contact me if any problem with the Dropbox, access to the videos and files, and if any question on that tutorials or on others. Okay. And with that, I say you goodbye. Yes.
Goodbye.
Yeah, I have a
Thank
small
you.
question.
Bye.
Oh, sorry, there is a question. Please go on.
No, sorry. No, I would like to know what was the shape of the pair correlation function for a polymer. Is
So
there like valuable information in it?
Because, in a sense, what we've seen, let me go back to, so we didn't do that specifically, but what we did is to get this relation, okay?
Mm-hmm.
So this is Gaussian.
Yeah.
Okay, so let me,
yeah.
okay, you see what I mean? Should I continue?
Yeah, so it will be
I stop
Gaussian
here?
then.
So it's a Gaussian, it's 1 plus a Gaussian, and you should do the Fourier transform of that. So you have a Dirac component due to the 1, okay, a factor, and then another Gaussian. Okay. Yeah. So you have all what you need. The Dirac aspect is related to the self. I mean, you know, in all those sums over m and n, let me just try to find one here. You see, in all those sums, m can be equal to n. So in a sense, you can also look at the correlation of the density at one point and at the same point. And this is exploding in a sense, okay? This is the Dirac aspect. Okay, but in any case, the main question you ask is, this is typically Gaussian.
Okay. And so G of R also, because then the Fourier transform is also Gaussian.
Yeah, so this is, what we had here was something like that for two specific monomers, but we had something like that, remember? So this will be indeed, all that will be a Fourier transform of a Gaussian, but you have to remove the Dirac here.
Yeah, okay.
Okay, but just do it and you will see it's mainly Gaussian what you want to have as an answer. Okay?
Yeah, thank you.
So it's a good remark, because you remember we were at some point trying to understand the effect of interactions. So starting from the ideal background, Okay, the monomers have the right to overlap, they don't interact, etc. We said, okay, no, now let us correct that vision by adding some, by reject the chains that are overlapping, for instance. And to do that, we said, well, okay, we do a simple estimate. We have a sphere. The radius of that sphere is the radius of gyration of your polymer. And inside the monomers, they are like beds equally distributed everywhere, like uniformly, so sharp and then 0 outside the sphere. Well, in fact, it's a Gaussian. The density correlation is a Gaussian. So it means that the density is reducing towards the edge, for instance, okay? And the correlation of the density is also exponentially, Gaussianly decaying. Okay? All right, any more questions? So if not, I wish you a very good weekend and see you next week. Bye-bye.